Hi everyone, this is Sarah with you here. We're going to look into Navier-Stokes equation. Navier-Stokes describes the motion of fluids. So how do we know when we can use this equation? When we care about the momentum and identifying the velocity profile, we want to use Navier-Stokes. So here it shows the overall equation, where little p is the density, big P is pressure, v is velocity, t is time, g is gravity, and mu is viscosity. Please note that the general equation lists the velocity and gravity as a vector, meaning that it can have more than one direction. For general understanding, we're going to look at the Cartesian coordinates, but please note that there are cylindrical and spherical coordinates as well. This is the breakdown of Navier-Stokes in the x, y, and z direction. We will focus on breaking down specifically the x direction of Navier-Stokes. At the end of this video, you should be able to identify the meaning of all parts of Navier-Stokes in the x direction and be able to carry that over to any direction or coordinate system you use. Here I have highlighted two parts of the equation that have given students the most difficulty in the past. Let us focus on the part of the equation identified as number 1. Here I have broken down the differential operator to identify 4 parts. In the first part, it is the change of the velocity in the x direction over the change in time. If we are solving a steady-state problem, we know that nothing is changing over time. Therefore, the velocity in the x direction cannot be changing with time, and equals 0. However, if our problem is unsteady, then this may not be eliminated from the equation. Next, we focus on the velocity in the x direction. If there is no velocity in the x direction, Vx equals 0. Similarly, this applies for velocity in the y direction and velocity in the z direction. Alright, here comes the tricky part. If velocity of x is not changing in the x direction, then dvx dx equals 0. This applies to dvx dy and dvx dz. But what does this mean and how can we identify it? Here is an example. In this image, velocity of the x direction is changing in the y direction. Therefore, dvx dy does not equal 0. Great, so now we figured out how to identify the left side of the equation. Now we will explain another part of the equation, which is labeled as number 2 here. Now looking at the Laplace operator of the velocity in the x direction, we have broken it down into 3 parts. We can apply our understanding of the left side of the Navier-Stokes equation here. Because d squared vx over dx squared is the derivative of dvx dx, then if dvx dx equals 0, so it is d squared vx over dx squared. We can apply this idea to all the parts. Congrats guys, we now understand when we can keep or remove certain parts of the overall Navier-Stokes equation in the x direction. This applies to the y and z direction as well. The overall video simply translates between the math and the meaning of the Navier-Stokes equation. I hope it helped, and good luck.